Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is Week 11, Part 3. For several years, chatbots have defined our primary interaction with AI. But deploying a standalone bot directly in front of your users fundamentally increases the massive risk of brand liability. This diagram shows the traditional deployment path. It's a simple linear flow. A user writes a prompt, the language model processes it, and an output is generated. This architecture is brittle because it relies entirely on the unpredictable nature of a raw text generator. Look at this flowchart comparing a traditional help desk to a chatbot. Replacing human pipelines with a single model is the chatbot fallacy. Mitigating this with human reviewers causes automation bias. Reviewers lose vigilance, allowing critical errors to slip past. This matrix plots application types by risk and autonomy. High autonomy agents act within their environments rather than just generating text. Because they execute actions, the architectural design of the surrounding system matters exactly as much as your choice of model. Software 3.0 uses a composite system architecture. Here, the language model functions as a central reasoning engine, securely surrounded by API gateways, memory states, and safety verifiers. Reliable machine pipelines cannot process free-form prose. They require strict, schema-validated objects. You achieve this through two structural primitives. Function calling triggers external actions, while JSON schema outputs clean, predictable data fields, like category and urgency for downstream formatting. This pipeline illustrates retrieval-augmented generation, or RAG. Models lack dynamic facts, so a RAG system indexes your external documents and injects non-parametric knowledge, data that isn't stored in the model's fixed weights, directly into the context before the AI answers. By enforcing strict data structures and grounding the model's answers in retrieved evidence, we mitigate the primary drivers of hallucination. This establishes a predictable baseline for enterprise software. Before any text is generated, incoming prompts can be converted into embeddings, dense mathematical vectors that capture the semantic meaning of the words. This allows fast, classic machine learning to triage the workload instantly. This slide outlines how we deploy those vectors. Clustering algorithms like HDBS-CAN group similar prompts together to identify systemic issues. On the other end, isolation forests, algorithms designed to detect anomalies, flag novel outlier inputs that require immediate human escalation. Once routed, the system enters an agentic workflow. The AI observes its current state, makes a decision, and executes an action. This iterative loop allows the agent to recursively break down massive goals into executable steps, self-correcting along the way. The AI operates as a proactive reasoning engine, capable of sustained problem-solving over time. For autonomous agents to safely interact with external systems, they require standardized connectivity. The Model Context Protocol acts as a universal adapter. It standardizes how models discover executable tools, resources, and specific prompts, removing the need for custom-coded integrations. This flowchart details the agent-to-agent protocol. A2A provides a shared language that allows multiple specialized bots, like distinct HR, finance, and compliance agents, to discover each other, match capabilities, and delegate subtasks within a swarm. This schematic illustrates the multimodal frontier. By combining universal tool access with multimodal inputs, allowing models to parse both text and visual UI layouts, we can deploy an ecosystem of collaborative digital workers. This diagram demonstrates a different approach. Traditional human review fails under automation bias, so we invert the loop, using the model as supervisor. The human does primary work. The model acts as a second set of eyes, notifying the worker of abnormal proposed solutions. These crossed-out graphs show the rigorous demands of LLM-ops. Unlike traditional software, language models introduce non-determinism, meaning the exact same input can yield wildly different probabilities on sequential runs. Because of this, standard evaluation plots fail. This chart illustrates how engineers evaluate AI in production. They calculate statistical distributions over test runs, comparing a champion model against a challenger model. They apply significance testing to determine if results are caused by chance, proving if a new design genuinely outperforms the old. This grid outlines the daily reality of production architecture. Engineers constantly navigate trade-offs, balancing context windows against better retrieval and raw generation against strict tool use. Scaling open-ended intelligence in the real world ultimately relies on rigorous grounding, structured data, and meticulous system design.